Hello, my name is Alias Arab, and today I'm going to present my work with my colleague Ilya Hadzik at Nokia Bell Labs and my PhD advisor, Professor Jingeng Gi. I'm a robotic researcher working with Nokia Bell Labs and recently finished my PhD at Rutgers University Department of Mechanical and Aerospace Engineering. And the title of this work is Safe Predictive Control of Four-Wheel Mobile Robots with Independent Steering and Drive. Let's discuss about the motivations of this work. The rise of autonomous mobile robots and their existence alongside human has left a huge gap in simultaneous robot safety and performance assurance. Unlike the previous AGVs or automated guided vehicles that was being used in the industry for like longer than 2-3 decades. They were following predetermined path, and the safety of this type of industrial robots was just like stopping if there is a human in front of them. But safety assured and smooth robots motion will increase the social acceptance of the robots in future, and the future control strategies should be able to adaptively guarantee the complex safety constraints in real time. So the purpose of this work is introducing a control strategy that is able to apply this type of constraints, and we can possibly change the danger robot in operation sign with robots are safe signs in future. And the objectives of this work are: we define a proper robot human safety constraint for human robot interactions. We design a flexible formulation capable of adjustable pose of desired performance and required safety. And also we discuss adaptive mobile robots do not follow a strictly defined path unlike AGVs, and multi-objective safety guaranteed control of autonomous mobile robots in real time is needed to operate robots within inches of human. So this is the strategy that we propose in this paper. So any autonomous mobile robot working on any given environment has multiple layers. The perception layer, control layer, and decision making and planning layer. So the place that we are discussing that we can apply these safety constraints to the robot, which increases the safety of the robot more than any other layer, comparing to the motion planning layer or to the map, which is like based on the zone. It's on the motion controller layer, which is in real time. Previously, it was just like a 0 and 1 type of safety constraint that the robot's motor would stop if it was a human in front of the robot. But a more advanced type of safety that can also guarantee the performance of the robot is a predictive type of controller that we can apply more complex constraints to the system. The robot's dynamic is complicated, and also we need to apply complex constraints to the motion of the robot, and also the dynamic of the robot is also constrained to the inputs and state constraints as well. Model predictive controller or nonlinear model predictive controller is proved to apply very complex type of constraints in real time. So the safety constraints that we define for our human-centric control is basically using the relative location and velocity of the human and robot in real time. So the assumption here is that we are able to detect the human and robot's location, orientation, and speed within a given environment. And the robot's goal here is to reach to the green point when there are like humans on the middle of the way, and the robot shouldn't break the human line and shouldn't get too close to them. And if the robot is close to human, it should keep the safe velocity and acceleration. And the overall safety set is the combination of all the safety sets for any individual. The safety rules basically are defined in the table here. The robot going from a given point to a desired point shouldn't get inside the safety bubbles around the human. These safety bubbles are a smaller circle and a bigger circle. The bigger circle is to the front of the human, so the robot wouldn't break the human's line, and the smaller circle is to keep the robot outside of safety zone around the human. And also, we are calling this as a keep distance from human and yield to humans. And also, we need to limit the speed near human. If the robot is getting closer to human, the speed of the robot should be adjustable to that distance. And the acceleration of the robot relatively to human should be acceptable, that wouldn't scare or cause fear around human. And why did we choose nonlinear model predictive controller? So the reason that we choose this controller is its strength on applying very complex constraints in real time. The objective of this controller is to reducing the tracking error or getting close to the target with the least amount of change in the input. So it means the input of the system should be very continuous. And the derivative of that tracking error, it will also keep the motion of the robot smooth. We can adjust this objective and have a multi-objective optimization that can give us different solutions in future. And also we are able to apply safety constraints by adding this penalty function to our optimization cost function. So this optimal control problem, unlike the traditional optimal control methods, is able to apply complex state and input constraints in real time. So the optimization problem is subjected to the dynamic of the robot. We know the uncertainties range in real time, and we want to keep the barrier function of the safety barrier functions inside the safe set that we define in the table. And the inputs of the system, which are the steering wheel of each wheel, the speed of each wheel, are also limited. And we want to keep the side slip angle of each wheel, which is causing unnecessary friction in real time, close to zero, always equal to zero. So it means we don't want to have any agile maneuvers and also any unacceptable maneuvers dynamically. And we are able to predict the future states of the robot by simulating this the dynamic of the robot and the environment within the prediction horizon. So here is a demonstration of a 4 independent wheel type of robot. Each wheel is able to rotate independently. It can cause torques by the internal electric motors added to each wheel. The tire and road interaction is highly nonlinear. We are using magic formula to model this tire road interaction. The kinematic of the robot contains uncertainties, and we added those uncertainties to our simulation. And the dynamic of the robot relates the tire forces to the acceleration of the robot. We also embedded the actuators model into our modeling as well, where the voltage of the motors will cause the torque and velocity of each wheel. So here is the full state space of the robot. There are 8 inputs and 10 states for this robot, and the system is highly overactuated, 8 inputs and 3 degrees of freedom. We have 5 degrees of overactuation on this system. And here are like the results when the robot is trying to get to the target. There are 2 humans facing each other in the middle of the way, and the robot will bypass them smoothly. And you can see on the figure on top, the robot will get to the target without getting close to human. And here, all like on the left, you can see the robot starts from different initial point, and it will not get close to human when it reaches the target as smooth and fast as possible. And on the left, you can see between time 7 to 9, there are some oscillations which is caused by the external disturbances that we added to the voltage and sensor data. And as a conclusion, this work demonstrates we are able to apply safety constraints for human-centric environments, and we can embed these safety constraints directly to the controller. And the controller produces robust and efficient motion, and we are able to implement controllable functions as safety constraints to our nonlinear model predictive controller. And we implemented and validated our work with simulations in MATLAB and Gazebo. And in future, we will test these algorithms on real robots for more validations in more realistic environment, and want to integrate this work with motion planner and local planners. And we would say thanks to all the colleagues that helped us on preparing this work, the hardwares, and giving us really good content. Thank you. Please ask if there are any questions.